Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are thrilled to have Christos Papadimitriou here for his annual, or sometimes even more than annual, visit. And for once, I guess he will not be talking about game theory, which we love hearing about, but he's been sending us his students and stuff who tell us about that. So this time he's going to be talking about a different topic, which is linked decompositions and Polya Urns. Oh, and for those of you who want to talk to Christos, he's here through next Tuesday. Okay.
Hello, everybody. Henry Lin is my student at Berkeley. Martha Sideri teaches computer science in Greece. Christos Amanatidis is her student. And Dick Karp is Dick Karp. Okay? Let me try to set the context. As sort of challenges of scale accumulate in the internet, there are several projects. More and more people are thinking about crazy ideas of how to replace the internet protocol. Okay, and the craziest of these ideas, think about routing without IP addresses. All right, without sort of the structured hierarchical IP addresses. So, sort of roughly the dream is the following. Imagine that you log in on your laptop, you get a random 200-bit string. Then you work for a while, and after 10 minutes, the internet knows how to route you. Okay, so to this particular address. All right, so the closest sort of the inspiration for the remote inspiration, sort of it's for what I'm going to tell you comes from a paper by a bunch of people, including Schenker and Stoika. And the students, which sort of the work is called ROFL, routing on flat labels, is sort of the idea that I told you, and it's inspired from peer-to-peer systems. Okay, so the methods they use has this flavor, and they experimented with it, and they have some very cute, very nice ideas, clever ideas about routing. And when they explained it to me, what happened is I was trying to think, okay, what is the theoretical idea here? I mean, when I try to take this idea and push it to its absurd extreme, okay, so that's what I'm going to tell you about, all right? So there is another sort of there is another bunch of work, another research tradition called compact routing. Where basically works in any graph, and it builds sort of routing tables of size square root of n. So the graph has n nodes, so the nodes don't need to know about the routing tables, don't need to know about every node in the graph. And despite this handicap, they find paths that are close to shortest, at most 3 times the shortest path. That's called a stretch. All right. So one of the key papers here is due to Thorup and Zvik. Okay, and there is a real sort of a lot of papers on this. So if you think our algorithms are as routing algorithms, you shouldn't. Their performance is sort of similar to those and technically dominated by what the compact routing do. Okay. Okay. All right. So, okay. So we start. Imagine a network. All right. So what I'm going to do is I'm going to decompose it into 4 subnetworks. All right. So the 4 subnetworks have colors: red, white, blue, and yellow. And so the dots will have colors, all right? And some dots are going to have more than one color. So here they are. So here are the 4 components. And there are, the largest of them has 8 nodes. So no node belongs to more than 2 components. That's B, the overlap. There are 4 components. They inherit the diameter of the network. In other words, they don't worsen the diameter of the network. The diameter is 6. And here is the killer requirement. These networks are linked. Linked means the following, that any 2 subnetworks have a node in common. So the red and the blue, they have a node in common. Is this clear? So that's, so if you wish, no 3 of them intersect, all 2 of them intersect. Okay? So this is basically saying again what I told you, I think. So we are interested in B equals 2 and the diameter to be log n. All right? So, and this I'm not going to mention again. Essentially what you want to have about square root of n networks whose size is square root of n. So why is this the limit of our ambition? Here is why. Because you have these subnetworks, right? C subnetworks. Any 2 of them must intersect. They cannot intersect on the same point twice. No 2 of them can. So there must be at most square root of n networks, right? Because otherwise there is not enough points there to intersect. Okay. So at best we can hope for square root of n networks that have about square root of n nodes each. All right. And again we want any 2 of them to intersect. Okay. So that's the point is that if you can do this, you can route. You can route to the small tables. Here is why. Suppose that you want to send a message for a packet from the yellow node, this node to this node, all right? Okay, suppose first that you want to send a message from this node to this node. That's easy, okay? So the yellow subnetworks has a routing tables, they know how to send around. But imagine now that you want to send to this or that, okay? So you can do it as follows. First, you know that there is a node that is both blue and yellow. Well, you find this node, and it's non-trivial to find it. And then you have to do a data structure trick to find it easily. Or you can cheat as follows. You give up on the dream that the addresses are just flat, and you have sort of, half of the address says yellow or blue, okay? So if you have this, it's easy to do. But you can do it without that, okay? You can use a data structure trick that allows you to, which I'm not going to expand on, in order to go from here to there, you first go here, and then in the blue network you go there. Is this clear? So this is what we want to do. So wouldn't it be great if networks were like this? Okay, you could be decomposed this way. That's what I'm saying. All right, it's a fantastic fantastic property for networks to have. So the only question is, can we do this? All right. So, well, of course, it depends on the graph. Okay. So I can do it on the click, and you can do it on the path. Okay. So that's. If you are given a graph, can you do it? Of course, you can do it. You can't tell. All right. So here is a major surprise to us. I mean, we were hoping for this, but but it came as a major surprise. So there are ways there are ways now to download the internet topologies, or from various sites. Okay, and basically we did it for several variants of this. Let's say for the graph of the autonomous systems, and then
how big is the graph?
15,000 nodes. Yeah, 15,000 nodes. 15,000 nodes. And then we did it on another graph that have the router graph, which is like 50,000. Yeah. So what, we took this graph, 15,000 node graph, and we decompose it to 70 subnetworks, size between 100 and 300, and they all intersect.
Huh?
Okay. So I think this is impressive. Okay. So. one question is how
Prove to us
how that the internet, yeah. So the question is, what can I prove now, right? I mean, so I have this great sort of empirical result. Can I prove something? So we'll think about it, all right? So maybe, yeah. So I mean, one question that comes immediately to mind is it's an NP-complete problem. How did you apply? How did you find it on the 50th or the 15th or 50,000 node graph? Okay, the answer is we have a heuristic, and basically this talk is about the heuristic. Okay, so and it works. It worked for the internet. All right. So is clear so far? So we want to.
Do you have an idea of which kinds of graphs your heuristic?
That's what the talk is about. Yeah. So basically we suspect that this is not a coincidence. Okay? We think that all internet graphs have this very unlikely property. And the only challenge now is what is internet like. Okay? Over the past 10 years, people have proposed many models that are sort of internet-like graphs. Okay? And we sort of we tried several of them, and for 3-4 of them we were able to prove that yes, with high probability they have. And I'm going to tell you sort of the most interesting of this, all right, which is the preferential attachment graphs. So they were proposed 8 years ago by Barabasi et al. And have been studied sort of to death. Okay, so we know lots of things about them. So in fact, the best thing is to show you a movie of them. Okay. All right. Maybe not. Look how, okay, and of course it does. So pardon the Greek.
You're not supposed to say the obvious thing, right?
Pardon the Greek. Yes. So I'm not allowed. I'm not supposed to do the obvious joke, right? Come on, give me a break. Allow. Okay. So you're going to see a movie now when the beast has its pint of blood of me. Okay. Yeah. So you'll see a movie, and courtesy of Christos Amanatidis, and I can't slow it down, but that's okay because you'll see it many times. All right. So here's what's going on. Nodes arrive. All right. Every time a node arrives, it connects to 4 nodes in the graph. All right. So the first node has no option but to connect 4 times to itself, all right? And the second node has to connect either to itself or to the previous node. And to keep the picture clear, we omit parallel edges and self loops. But we remember them, okay, because they're important. Because they determine the degree of every node, all right? The real degree of every node. And now the point is that how are these nodes selected? I'm a new node. There are 10 other nodes who have arrived before me. How do I select this node?
The seed of the random number generator.
Sorry?
You refresh the seed.
Right, yeah. So what you get is the following. So the rule is the law is the following, that you connect to them with probability proportional to their degree. Okay? So the rich get richer and the poor get richer, but a little slowly. Okay? Is this clear? So this is what this process does. And these are the graphs that we're going to analyze. And now I want to stop this. from current slide. Okay, all right. Right. So, so this slide tells you the story of the preferential attachment model. So, in such graphs, so that's a conjecture. In such graphs, linked decomposition is possible with overlap 2, that's what we want, with small diameter, and with size of the components not too far above square root of n. That's the conjecture. And hopefully, with small m. M was 4 in the previous. I mean, you don't want to have too many edges. The reason is that the internet is sort of has a degree about 4. Okay, so you don't want to go much above 2. M equals 2. You know, if you want to be faithful to your ambition to say something about the internet. Okay. Okay. The question is, can we prove it? All right. So that's a conjecture, and the answer is a resounding yes. Okay. So in fact, 3 resounding yeses. Okay. So.
Is this like Jeopardy?
So, yes, you can prove it, but we need m log n, okay? So we need a huge degree. And then you get also an extra factor of square root log n for the number of nodes in every component. And you don't like that because m is large. Second answer, yes, you can prove it, but we need something called promiscuous nodes. Promiscuous nodes is basically a node. Every component is allowed to have one node that violates the B requirement. In other words, it can be part of many subnetworks. Okay, and then we need well, actually, recently we have improved this to square root of n log n also. So that's.
And what is many?
E
to the n square root of n.
Say again.
Log n.
Say again.
Which many?
Log n.
Where do you see many?
In the word promiscuous, I see a many, and this n many is log.
So no, many can be power of n, small power of n.
And the 2 there was trying to be a half, right? The n to the
Half, yeah.
Plus epsilon.
Half plus epsilon. Yes.
Unbelievably promiscuous.
Right. Yeah. And you don't want that, do you? So, in other words, we have to switch a little the definition of and we don't like that either. So the third proof is the best, but actually, as you know, last Friday was the Fox deadline, and a deadline like that can ruin a joke. So. Right now it's not quite, so we have finished the proof. Yeah, so. Okay, so.
You have to say
with what m?
Yeah. Okay. What is the basic structure of all 3 algorithms? We run the graph creation algorithm. In other words, and basically online we decide which component every node that arrives is going to be. Okay? What we do is we have sort of decided ahead of time about the number of components. Okay? And we just have to play with and then, so in the beginning we put everybody in one component only. Okay? And then towards the end, basically the last half edges, what we do, the last half arriving nodes, what we do is this. As they arrive, they connect to 2 components perhaps, okay? And then we say, have these 2 components been linked before? And the answer is no. All right, then this node will belong to both. And this node will be the one who is going to link these 2 components. Okay? And therefore, by Coupon's collector, okay, so the Coupon's collector is this sort of phenomenon in probability theory that if you sort of if you play bingo, you have to your table has to be hit 10 log n times before you bingo. Okay, so that's right. I mean, if you so that's but n log n will be enough, and so. So the point is that after C square log C steps, okay, you can be sure that you have connected all if these components were balanced and keep balanced throughout, okay? So and this will be the struggle, all right? So, okay, so I'm going to, I'm just giving you a preview of what the difficult part is to keep the components balanced.
Now you also did it for the real internet, so how did you do it there? Because this is not how you...
Excellent question, I'll tell you, yeah. So you see what he's asking? In the real internet, you don't see the nodes as they arrive, right? What do you do? Okay, so here is the quick answer. Well, we assume that the nodes arrived in decreasing degree. Okay, and then we run this algorithm, and it works, which is sort of actually likelihood or something.
They just gave two.
Yeah.
So what you described so far seems to lead to components of size square root of n log n.
No, it's square root of n over log n. Square root of n times log n. Yes, right.
Yeah.
Yeah.
So is that the result?
So why do I have this plus epsilon?
Or why? So is the third yes that you wrote below, the third yes that you had in the previous slide, what did it exactly state? Did it state that
it's
the size
square root of n plus epsilon. Yeah. So and we still need this. Okay.
M is equal to?
M here, so in my experiments M equals 2. With promiscuous nodes, M equals 2. Without promiscuous nodes, in the third algorithm, M has to be sort of, if you want your epsilon to be small, M has to be arbitrarily large, okay? If M equals 2, then we can do n to the 2/3.
If you do a simulation on the Barabashi graph,
yeah, so M equals 2 works better than, even better than, much better than what you can predict. Gives you exactly square root of n. Square root of n over 2.
So you believe that there should exist a proof out there that would give you...
Square root of n over 2, no. I think, I think the truth is square root of n. Okay? There should be a proof out there, and in fact we have one, so which gives you square root of n log n, but it has promiscuous nodes. Okay? And yes, there should be a proof out there that gets into the promiscuous node without harm of the exponent. Yuri.
also the almost surely part.
So what does it mean? It means with probability 1 minus 1 over a power of n. And it's usually square root or fourth root.
And this you don't trade against steps?
No, this you don't trade against. Okay. So, all right. So I explained what coupons collector means. That basically what happens is that you have C-square pairs. It's like collecting pairs, okay, of components. And in order to make sure that you hit all pairs, you must go for C square log n node. So that's basically the idea. Okay, so I'll skip algorithm 1, the first proof, so that uses log m edges per node. So we'll go to this, which is sort of, gives you the square root of n log n, but has promiscuous nodes, and just two edges, a small degree. So here is the, okay, promiscuous nodes basically are these. They belong to many components. You allow one such node per component, okay? There is only one node. And these nodes are confused during routing, okay, because they belong to too many networks and they hear things from everywhere. Okay, so basically you have to route around them. Okay, when somebody receives a message, and it does make sense, he says, "Oh, okay, it's from stupid. All right, so I'll do something special here." So and this is and it's quite easy to route around them. They're not a big problem in routing. All right, so how do you do this? Well, You run the algorithm for about C square nodes, where C is the number of components that you have already decided. And then what you do is you find a breadth-first search tree of the nodes so far. This breadth-first search tree, you know that it has small diameter, and you want to preserve it, that's why you do breadth-first search. And then what you want to do is you decompose C into C approximately balanced components, disjoint except for one node per component. Okay? So, so you decompose this breadth-first search tree into components that are approximately balanced within a factor of 3 of each other. And these components may have one node in common, okay, 2 consecutive components. And that's going to be the promiscuous node of that component. And this dynamic programming, rather straightforward dynamic programming. Okay? And then once you have these, they're balanced. And it turns out we have a lemma that says that if they're balanced at the beginning, they'll continue to be balanced. Then you can do coupons collector. And you connect to the next C square log n node, log C nodes. So that's the algorithm 2, and that's the second proof. And the main part of my talk is about algorithm 3. Okay? Algorithm 3 sort of, is the general algorithm. What we do is we run the graph for about C square plus epsilon nodes. And basically what we do, okay, remember, what we are agonizing about here, right? We want to keep the components balanced, all right? So, a new node arrived, it connected to 2 components. The question is, to whom we are going to give it? Remember, we want to keep it balanced. So, we're going to give it to the smallest one, to one that has the smallest total degree, because the total degree, the sum of the degrees, is basically the attractiveness of the component, okay? How much it attracts, and you want to keep this balanced. And of course, it's a proxy for the number of nodes, okay? So it's fantastically, it's expedient. It's a good thing to try to balance, to give it to the smallest node. And the components now are balanced, it turns out, okay? That's the main result, okay? And then you continue for another C square log n nodes to connect. And in fact, the algorithm, which is the algorithm we run on the internet, and also in such graphs or all kinds of graphs without knowing how they were produced, they interleave the 2 phases. Okay, so if opportunistically, it may connect some components even very early, even though to prove anything, sort of, you have to not do that. Okay, so yeah, Yuri.
You seem to imply that it works in linear time. Is it correct?
Yeah. Yes. Yeah.
Online.
Online. Yeah. But you have to be there when the network is created. Okay.
Right.
Okay. So each node is component. So every node is component to component J, with probability which is proportional to the total degree of J. Okay, the sum of the degrees. That's its attractiveness. And in doing so, it increases the total degree of component J. It turns out by n plus 1. Okay? And this recalls Polya Urns. So this is where I'm going to stop again and show you the next moving. Polya Urns. What's Polya Urns? Okay, it's balls in bins. All right, and we know that if you throw balls in bins, things are going to be very balanced. Okay, because sort of probability works in your favor. Polya Urns is sort of a model that has been proposed explicitly. Give me a break. Sorry?
I think it's sinking in the back.
You think so?
Yeah.
and thought about me for a while, and then said enough of this guy.
Okay, I think if you just leave, don't start it again because it'll just start thinking again with its
Okay.
little brain.
Okay, all right. So what is Polya Urns? Okay, because I may have to show it to you on the blackboard, which would be a pity. Okay, so imagine you have balls in bins. The new ball arrives. Okay. Not refrain from clicking on it. Yeah.
Ah, now it's bigger than it was. Oh. Right.
Maybe the file is too big.
No. They know it opened a few times.
Pull up the task manager.
And the stupid mouse is not working.
No, I think it's XP.
You're in the right place.
Okay.
Okay, why don't you explain it on the board?
Yeah. Okay. So a new ball arrives, and the point is where it's going to go in. Okay. And the Polya Urns in balls in bins, it will go sort of everywhere with equal probability. Here it will go to this with probability to every bin with probability proportional to the current occupancy of the bin. Is this clear? So for example, it has twice the chance of getting to this ball, to this bin than to the other. Okay? Okay, excellent. So yeah. Now we only have to override the, yeah. Okay, so, all right. Enough said. All right, so think of the balls as magnetic, okay? And bins with high occupancy attract the balls more, okay? So the rich get very rich, all right? So this is supposed to model processes that create imbalances, all right? In some sense, or if you heard this literature about power laws, I mean, this is the baby instance of the creation of power law, okay, of imbalances, sort of, and not concentrated distributions, okay. Even though, strictly speaking, does not create a power law. All right, so this is. And in some sense, our process, so I can start trying to get rid of it. Yeah. I was giving a talk once, and a big thing appeared on the screen, and somebody from the audience shouted, "Escape!" And I ran to the door. Yes. Okay. So basically, what I'm saying is that when you add nodes to the components, essentially you have a Polya Urn, except that you have a choice. All right. So you draw two Polya Urns. I mean, so the next dollar sort of draws two people. Sort of one is super rich, the other is upper middle class. Sort of prefers the upper middle class. Okay. So the rich so the rich get richer, but not as fast as in the Polya Urns. Okay. So you have Polya Urns with choice, and the important question here is do Polya Urns with choice
the ratios end up being constant.
No, they don't. If you have n Polya Urns, if you have n urns, if you have n urns, and you throw n cubed balls, the smallest one will be n, the largest one will be n squared log n. Okay? Yeah.
If you're creating a new...
And here, of course, we're creating lots. Okay? Yeah.
There was a constant number of...
Constant, yes. Right. Yeah. The function of constants are always constant, yes. Okay, so so this is Polya Urns with the power of choice. So every ball picks two urns and then chooses the smallest one. Okay, but it picks it well. So the point is that now
You lose a lot of the nice independence of Polya Urns, or do you not? Are you still able to get results where you basically can pick a parameter at the beginning?
So you know, in some sense, think about it, okay? We don't have a choice, right? I mean, this is our model. This is what happens. This is what happens in our model, in an algorithm, okay? So even if we don't like it, we have to study it. Right? Yeah. Okay. Yeah. And number two, it's beautiful, okay? It's really, yeah.
So you choose two urns proportional to the number of balls.
Exactly. Yeah.
And then take the small.
To the smaller one of them. Yeah.
Can you choose this?
So the point is, if you notice, so you know that for example, now this guy will very rarely get a ball, right? But now these two guys will sort of, and in the end, they do balance, okay? But you have to throw 500 balls in order for them to balance, to come close to balancing. So the question is, all right, maybe they balance, but do they balance in exponential time? Do they balance polynomial time, or what? Okay? We prove they balance in quadratic time, okay? And they cannot balance any faster. Quadratic is the number of urns. Make sense? So when I say balance, I mean something strong. They balance within 1 plus or minus epsilon of each other. They're really equal, almost equal. All right? That's a hardware problem, I know. What I can do?
I'll control whatever.
When the mouse heard about the new mouse, immediately said, okay. I'm going to be replaced. Right. Okay. Okay, so here is our main theorem. If n urns are started with about order of n balls, with at least one ball in each, then after n to the 2 plus epsilon balls, with at least 2 choices. So basically, to get m small, the epsilon becomes 1. Okay, that's to get n equals 2. Epsilon goes up right now in our proof.
And is that epsilon plus minus epsilon, that epsilon the same?
The same, yeah. You can take this. Yeah. What do we?
Now, do you believe that this is short, or is that...
So you cannot go below 2. Yeah, and sort of, and somebody will come up with a n square, clean n squares argument. That's
n squared for...
Yeah.
Either it's
for 2 balls. Yeah.
Have you done some simulation?
Yeah. So so we have done very extensive simulations, and it's unclear if it's exactly quadratic or what. Yeah.
Yeah. Is it n to the 2 plus 1 over epsilon or 1 plus epsilon?
So
you find the right trade-off, sort of,
For every epsilon there exists n.
Yeah. For every epsilon there exists an n such that m such that this. Yeah. Okay. Okay. So that's the main theorem, and I'm going to sketch it for you. To sketch the proof. So when somebody, when a friend tells me that they have proved something, okay, I usually say, wow, you can prove this? What's the idea? And usually what I get back is the following: oh, forget it. It's 20 pages of math. It's very, very complicated. So when I nod my head, but really what I want to say is, okay, I'm not disputing that you are a genius. Okay, but what I'm telling you is that there must be something you can tell me in 2 minutes, and I will know much more about the proof than I know now. Okay, so so that's what I'm going to do to you.
Do we have to tell you you're a genius?
before I start. Yeah. Okay, but it's 15 pages of math. Okay, so, all right, so we have to say that my students are geniuses, right? So okay. So first of all, okay. 0 point. Why don't there is for those of you who have worked on such problems, there is something called the differential equation method, so where you write an ODE, and we know the ODE. It's trivial to solve. It's much simpler than usual. It gives the right answer. We don't know how to bound its deviation from the answer. Okay, so we do something which is rather ad hoc. Okay, so the first thing we do is we weaken slightly the power of choice. Okay, so what we say is the following. We consider sort of finitely many types of urns, usually 2 or 3. And so we prefer low urns to medium, we prefer medium urns to high, but if we have too medium or too high or too low, we flip a coin, okay, we don't care much. Okay, so, and this makes our life a little easier, and you can show easily that if this balances, then our balances more. Okay? Dominates. So 2 phases. In first phase is like preliminary. What you do is you throw in half the balls, let's say, and we prefer low urns to high, where low means that it has like there is a fair share, all right, and if it has half of its fair share or less, that's low. Okay, and the others are high. And you do this for half the balls, and after phase A, it turns out that everybody has a lot of balls, and nobody has more than 10%, let's say, of its fair share. So now comes phase B, which sort of is the tricky one. You pick one urn, okay? That urn is going to be very important. That's urn M.
You mean minus delta? What do you mean? On the previous slide, last
yeah.
slide.
How can I have a fraction larger than one of the balls?
Then, so I cannot have...
Oops, back.
That fraction
so
back. One more.
It's times its fair share.
Oh, times its fair share.
So it cannot have more than one delta fraction of the balls that it should have, right? Yeah. Yeah, it should have, yes, right, yeah. Yeah. Okay? Okay, now, you pick M to be the 10th percentile urn. Okay, and this will stay with you forever. It's an important urn. All right? And in phase B, in the beginning, M is the medium urn, one medium urn. Everything which is smaller than it is low, and everything which is bigger than it is high. Okay, and ties, don't worry about them. So you start running. So here's what's going on. Imagine that this is M, okay? And it goes up and up and up and so on. Okay, that's M. The point is that if another, so now take another urn. If it ever touches M, then immediately this becomes medium also. Okay? The same for this, okay? If this touches them, and even if it shoots up immediately after that, okay, it becomes medium. Okay, so a medium urn is an urn which at some point in the past has had equal size with M. All right, and the rule is that we prefer low urns to medium and medium to high, and other than that we flip coins. And with high probability, after enough balls, all urns are medium. That's the key. That's the key result.
So all urns have touched
Have touched them.
this.
Yeah.
Now you have n urns, right?
You have n urns, yes.
And you start with roughly n balls in each urn.
Before phase 1. After phase 1, after phase A.
So in other words, you only have to multiply the number of balls in each bin by n to the epsilon, and you are balanced.
Wait. No, but in the beginning it could be unbalanced, okay? And
So in the beginning it's very unbalanced, but they have most n in each of them.
true.
And so I could think, for example, maybe I have n and n over 1,000 and
1.
1. And then, so I have a total of n squared balls already.
When are you
Starting.
At the end.
No, at the beginning.
In the beginning.
of what? And the beginning of what? Of
Total.
no, I have n balls. In the beginning I have n balls.
Oh, they
doing
distributed
this as he
Arbitrarily.
over all them.
Right.
I see you have to grow to n squared balls.
Right. Yeah. So the first phase, I throw in half the balls, and I get something. Okay. So I get a slightly more balanced distribution, and then I throw in the other half, and I watch very carefully what M does, and what everybody else does vis-a-vis M. Okay. And the lemma says that in the end of all this, everybody has touched them. Okay? And then comes another lemma, which sort of saved our skin for many times in this theorem. And actually, we used it in the other algorithms also. Once two large urns are equal, if they're large enough, then they stay close. Okay.
Oh, that's just Polya's urn.
Right, yeah. That's QED. That's the end of the proof now. Because everything has touched them, they were big already, so in the end they're balanced. Okay? Okay. Is this the end, okay? Not quite. I mean, this we had sort of over last summer. Okay, so and there was we loved this result, but it was about Polya Urns. It was not about our algorithm. Okay, so here is what the problem is. That at each step of our algorithm, M components are chosen at random, and the node is added to one with the smallest total degree. I'm just repeating the algorithm. All right, so among all these moderately rich people, we pick the poorest and give him the node, okay? And the degree of the smallest one increases by m plus 1, all right? What's the problem? The problem is that everybody else's degree is increased by 1, okay? So, you see what I'm saying? The other people have been touched by edges, okay, from this guy. And therefore, they have gotten something, okay? This guy got 3 edges, but everybody else got 1. Okay, so it's harder for him to catch up. Okay, because this guy is sort of, and this has been torturous for 9 months. Okay, sort of, and it's sort of in the end, it's not sort of a terrific modification over. So I have been giving this, this will be the humiliating slide for my talk, but now we just prove it. Okay, that this stupid modification also works.
Is there a new idea? Or
yes, I mean, so there is a new lemma. Yes, there is a new sort of crucial lemma, and you have to do everything a little more carefully. Yeah. So I have not updated my slides sort of, with sort of...
Tell me 1 minute more than...
yeah.
Yeah, to tell him.
Yeah. It's
a great population.
Don't forget my students, okay? Okay. So what can I say? Well, if something comes to mind, I'll say. So in our experiments we do this. In all of these graphs it seems to be give a's square root of n. Square root of n over 2 within the square within the so it's an amazing fit sort of with the parabola. So it's and the same for internet graphs. And for the internet graphs that are downloaded, we assume that the arrival order is that of decreasing degree. Okay, since we were not there when the internet was formed.
Does that work better? So if you did, now you could do the following experiment. You could run your Barabashi graph, and once it's done,
yes,
you could sort of...
We have run this experiment, yes.
Does this work better than the one which you do?
So I have to check the paper, but there is an amazing thing. I mean, it's very funny you ask this. That for some, in half the cases, ex post works better than online.
But only...
Yeah. So so for some cases, I forget. Maybe for m equals 4 it works better. For m equals 2 it works worse.
Oh,
yeah.
So
not random half. Not random half. Yeah. So for yeah.
One case.
For one case, yes. Yeah. So I'm curious why how it's we are trying to understand what's going on. The other thing is that we do routing on these networks, and 95% of the time the stretch is less than 3, and it's always less than 4. Okay, so we don't lose experimentally. If these guys can prove it, we don't lose much over the compact routing stretch people. Okay, so here is an extra result which just came in. Very simple idea, and it gives you routing tables, much better algorithm, much better routing algorithm. So can we do routing tables less than square root of n? The answer is yes, we can. So here is the idea, and sort of I'm not going to. So suppose that we don't insist. So we go away from linked decomposition. Okay, we don't insist that all subnetworks intersect. All right, and the intersection graph is not a clique, but the intersection graph has diameter too. Okay, now routing is still possible, but now we need to know the color of the subnetworks, and the routing tables are n to the third cube of n, and the point is that you can still decompose. With high probability, you can still decompose graphs like that, and you can decompose the internet like that. And for the proof now, you need the other cliché in the theory of probability, the birthday paradox. Okay, basically. So remember, okay, the diameter has to be 2. So this means that 2 components either they have to be connected, or they must have a third component which is connected. Okay, so the point is that as they get more and more connected with other components, the birthday paradox says that they're going to have a common intersection. Okay, that's what the birthday paradox says. That if you have square root of n, 2 sets of size square root of n, they're going to be intersect. There's going to have an intersection, and then this will happen sort of by union for all pairs, and that's it. So you really get cube root of n routing tables.
You can get any power by making the diameter.
We don't.
Yes, we don't.
See, because he used the square root of n in the birth.
And
You should be able to.
No, we haven't. Yeah, you should be able to decompose.
Yeah.
I don't know how to do routing if the diameter is 3. Because because now there are so many, so I'm in a network, right? There are, this is my world, all right? The point is that there are a number of networks out there which is the cube of the number of people in my network, okay? And I cannot know about all of them. There is no way to store information about, not even how to find one of them, okay? So there are other things you could have, you could cluster networks and so on, I have not, I suspect that there could be some, in principle, something that you can go down to the powers, yeah, but right. Okay, so open questions. Polya Urns with 2 choices in quadratic time. That would be a great result.
Now you have this in cube.
2 choices, it's NQ. Yes.
Mr. Epsilon was born in that.
So do all expanders have a linked decomposition? That's a great conjecture. Okay. So it turns out that the internet and all internet-like graphs that we have seen, they are expanders. Okay. That's actually not easy to prove, but it has been, it's a paper by Saberi, Milena, Michael, and myself. So we don't know. So all the results we have, they will be generalized by this theorem. So that in any expander you can have a linked decomposition. So maybe you have to assume something. Another question, if you want to have any pretenses of practicality, in realism, you have to at least study how a linked decomposition would change in the face of growth and especially failures. Okay. If nodes and edges fail. Yeah. So how can you repair? So in the internet you find alternate routes, but now you have split the internet. Maybe you lose alternate. Maybe you have to be much more careful.
There are also some nodes that drop, not only
drop.
Not only add.
Of course, definitely. Yes, right. Yeah.
So have you looked at a dynamic version of your algorithm? The nodes come and go?
Yeah. No. Yeah, good question. Yeah.
Half of it you have.
Sorry?
I have looked at the count, but not at the goal.
Right, exactly. Yeah. You're halfway there, right. Yeah. And a great question, of course, is how do you convince these autonomous systems, to
There's some game theory after.
Exactly. Yeah.
He had to put in game theory in the last line.
Right. Conclusions. Besides many open problems, it works for other scalable, for other models. Congestion seems to be a problem, but we have ways of taking care of it, both experimentally and theoretically. And this model may be useful.
You know about the Cleopas graphs they haven't been rigorously complicated models haven't been rigorously analyzed, but they have an Erdős range type process with new edges coming in, connecting, and then they you put in instead of one edge, you put a pair of edges, and when the pair of edges come in, but you only put in the edge where the product of the two components is connected is smaller.
But more generally, actually, can you come up with a strategy so that you make it short? You are my adversary. You always choose the one of those to delay.
Right. So the general so-called, this is again, Joel gave it this name because Dimitris was the one who was first investigating these, where these are random graph processes with choice.
I see.
But put in the edge, you get
Sorry, again, you put the, so you do GNP and
You try to delay the growth of the
growth of the giant component. Yeah.
So we do GNP, I give you two edges.
Okay.
You actually, both of them I choose at random, but then you throw the one out to screw me up.
Okay, yeah. I think I've heard about this. Yeah, right. Yeah.
So it's somehow philosophically.
Yeah, related. Yeah, it's the other way. Yeah, you're right.
About the routing, I mean, you always, for any two components, you route through the same node. So
Yeah. So no. For any two components, there is a different node.
Yeah,
but for this, right? Yeah. So on the other hand, so there are about C square sort of pairs of nodes in these two components. There are about A square. But then that's n. So so it's okay. You know what I'm saying? So this means it's balanced.
Because that node is
yes,
huge.
But every node is a linked node, right? You have square root of n components, so almost every node is a linked node. So it's not right. You see what I'm saying?
Linked node to some other color.
Okay.
So half the nodes are linked nodes. So it's not
In the promiscuous node.
Yeah. So but the promiscuous don't do any routing. So the promiscuous nodes are okay.
Just internal routing.
Yeah.
Internal routing.
So they have to do some kind of weak form of internal routing. Yeah.
Yeah, within the.
So they broadcast to all their neighbors. So whenever something happens, basically the promiscuous node says to everybody, "Oh my God, I received this. I don't know what to do. Help me." And they will know what to do. Yeah.
So does this mean that all ISPs have to be roughly the same size?
No, not at all. Not at all. So all this works with weights. And in fact, if you think about it, the degree of the node is a good proxy for size. Okay, so they're not at all the same size. There are vast differences in size in this graph.
Have you thought about trying to select all the number theoretic expanders? So you have this conjecture that this should work for any expander.
Yeah.
And have you thought about trying all the number?
So I wouldn't call it a conjecture yet. So I have this suspicion that it could. I guess I have this aesthetic sort of point of view that would be a great generalization of all this theorem.
A direction.
Yeah.
A direction.
Yeah.
So have you tried doing a number theoretic expander like the Q Urns?
No. For example, in a number theory expander, so you could actually do it, that would be fantastic.
Because it would be a different sort of flavor of where it's coming from.
Absolutely, yeah. No, we haven't tried that. Yeah, good idea.